is trig functions filmed before a live studio audience. Okay. Now I don't want to show you that much about that. Hold on. Okay. So do you remember when you did polynomial functions back in your last class, and you talked about what it was that made something a function? It was a test you had to perform. Vertical line test. Okay. So if you think back to just the most basic parent function there is, which is, what's the name of this function? Y equals x. Okay, so you think back to y equals x. How do you know that this is a function? It passes the vertical line test. Okay. Well, how do I know whether a function has an inverse? It has to also pass the horizontal line test. So I draw horizontal lines and I say, yep, it passes the horizontal line test. When that happens, we say that the function is 1 to 1. If a function is 1 to 1, then it has an inverse. And what you guys may have done in algebra is you took a function, you switched the x's and the y's, and then you solve for y. Does that sound familiar? All right, so what is the inverse of y equals x? X equals y. And so if I had the ordered pairs, all I would need to do is switch the ordered pairs. And I would need to take the domain of the first function, and it would become the range of the second function, and vice versa. Okay? Well, we're doing this not for a polynomial function, but we're doing it for the three basic trig functions, sine, cosine, and tangent. All right? Think about the sine graph that we did together with the yarn. So if you remember when we graphed sine, we started our graphs at 0 pi, and we went all the way to 2 pi. Okay? And then we know that it continues forever and ever in either direction. We just cut it off at 0 to 2 pi. We're just showing you right on the unit circle. And so this passes the vertical line test. That's not a problem, and that's why we call it the function of sine. But does it pass the horizontal line test? Not at all. At every peak or valley, it crosses twice, which means that it fails the horizontal line test as it is. But is there a way for us to restrict the range such that we really do have a one-to-one function? Is there any location that you can think of on that graph? If I restricted it, if I gave it a limit, that I could actually have a one-to-one function where it would pass the vertical line test and the horizontal line test. Well, give me a specific location. Tell me specifically from what angle to what angle you want to restrict it to.
Pi over for multiples of pi over 2 and multiples of 3.1.
You're close. You have the right idea. Anybody else want to try? He's got the right idea. He's got the right angle. It's just the wrong location. See that area right there? Okay. If I go from this angle measurement right here to this angle measurement right here, that portion of the sine function is a one-to-one function, which means that it passes the vertical line test and it passes the horizontal line test. So basically what we're doing is a very basic calculus idea of setting limits. And you guys, you're familiar with limits. You break limits all the time. I mean, that's what being a teenager is, right? You think about the big picture, and then you think about ways to break it. That's what you do. That's your nature. Okay? You know what the speed limit is, right? In certain areas. And you try to break that limit. You try to redefine it. So what we're doing is we're setting the limit on the trig function for sine such that all of our answers have to come from negative pi over 2, because that's what that angle is, to pi over 2. From negative pi over 2 to positive pi over 2. So we're basically taking a set of rules that we already know. We've done sine, cosine, tangent. We know how to find those angles and their ratios using our hand. We know what the sine graph looks like, but now what we need to do is we need to think about it in a different way. We just are going to restrict the area, place where we can get our answers. So for sine, that restricted area is from negative pi over 2 to positive pi over 2. Okay, now, the way that you say this is the angle whose sine is. And actually it can be written in two different ways. You can write it as arc sine, or you can use the -1 like what you have on your calculator. So if you look at your calculator real quick, if you hit second sine, what comes up on your calculator? Sine to the -1. All right, it says the same thing. So in English, here's what that means. You ready? What angle has, that's what that says. What angle has, and then a specific trig ratio of. So if we're doing arc sine, then we would be saying what angle on the unit circle has a sine ratio of whatever they do. So we're basically working backwards. Instead of me asking you for the ratio for sine at 60 degrees, I'm going to give you the ratio, and you're going to give me the angle measure. So we're just working backwards. Okay, so now let's talk about the domain and range. Remember when we graphed the sine function and you told me that the range went as high as 1 and as low as -1? Well, since we're doing the inverse now, that is the domain. What was the range is now the domain. Well, in the parent function for sine, the domain was all real numbers. So why is that not the range? Why can I not make my range for an inverse all real numbers like I had the domain before? Because I had to restrict it to negative pi over 2 to positive pi over 2 so that I have a one-to-one function. And what that means is it passes the vertical line test and it passes the horizontal line test. All right, the notation. Have y'all seen notation like this before for domain and range? Some of you may have, some of you may not have. And I've got the other way that you're probably used to seeing it a little bit later in this presentation. This is called interval notation. So if you see brackets around numbers, that means those numbers are okay. They're included. So that is inclusive. So the domain for the inverse sine function can include numbers as low as -1 and as high as +1. And the range can include values as low as negative pi over 2 and as positive pi over 2. All right, let's sketch out what that looks like, though. So just do this for me. Sketch your x and y axis. Okay, now label the horizontal starting point as 0, pi. All right, what goes at the top? Pi over 2. We're only working in radian, not in degrees. So what goes down at the bottom? Okay, what would go down at the bottom, you're right, is 3 pi over 2. But we have to set this up so that it matches the restriction that we have for inverse. What is another way? Negative pi over 2. Remember when we did coterminal angles? So this is actually negative pi over 2. Now, if I wanted to sketch the way this looks, here's what I'll do. I'm going to put a closed circle here. I'm going to take the arrow all the way up to a closed circle here, and I'm going to label that arc sine. That means that any angles that I give you as an answer have to come from quadrant number 1 or quadrant number 4. However, is 7 pi over 4, which is at 315, is 7 pi over 4 an acceptable answer? Yes or no? It's not. Why isn't it? Why is 7 pi over 4 not acceptable? It's clearly in the fourth quadrant. Pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, fourth quadrant. It's outside of the interval pi over 2 and negative pi over 2. So what is another way that I could state 7 pi over 4 and be within this restriction? Negative pi over 4. Now that's an answer that I'll take. 7 pi over 4 won't work. It's outside the restriction. All right, let me give you another one. If I'm talking about sine, and I want to know where on the unit circle is an angle whose sine ratio is negative 1/2. So use your hand and show me sine is negative 1/2. Show me sine is 1/2. What finger did you put down? Your index finger, right? That's your 30-degree finger. Okay? So it's got to be a 30-degree reference angle. Where can sine be negative? Third and fourth quadrant, sine is negative. Can I get my answer out of the third quadrant? No. So I have to get my answer out of the fourth quadrant. So I know it's a 30-degree reference angle. I know it's got to be within the restriction of negative pi over 2 to positive pi over 2. What's the correct answer? Negative pi over 6. 11 pi over 6 won't work. Why? It's too big. It's outside of this restriction. This restriction runs from negative pi over 2 to positive pi over 2. So you're going to have to convert your answers to a coterminal angle that falls within those two quadrants. Okay? And why are we only working with these two quadrants again? Go back to the graph that I showed you.
Because if we're working with inverse functions, then we're still thinking that it's like on a right triangle, so it can't go over 90 degrees.
It can't go over 90 degrees. It can't go below negative 90 degrees. But on a graph, graphically speaking, a function has an inverse if it's 1 to 1. If it's 1 to 1, it passes the vertical line test and the horizontal line test. On the sine graph, if I just use the parent function, it's not 1 to 1 because it fails the horizontal line test. But if I restrict the range from here to here, then I'm in business. I actually have a 1 to 1 function. So this is where all of our answers are going to come from. Okay, let's try some examples. Let me get rid of this. Let's try some examples. Okay, 2 examples. The first one, and I want you to write how you say this, like the translation of this. I know that if I read it, it says arc sine 1/2 equals pi over 6. Here's what that says. What angle on the unit circle has a sine ratio of 1/2? What angle on the unit circle has a sine ratio of 1/2? So you take your hand and you make it show sine of 1/2. Sine equals 1/2. So what finger goes down? 30 degrees, right? 30 degrees is pi over 6. So if I reverse the way I say that, pi over 6 is the angle whose sine value is 1/2. I'm just simply reversing the thought of what you did before. Before, I gave you an angle and you gave me the ratio. Right? I would say pi over 4, cosine of pi over 4, you would give me the ratio, root 2 over 2. Now I'm giving you the ratio and you have to give me the angle. It's just reverse. What angle on the unit circle, and in this case, has the sine ratio of 1 over 2? Before, when we learned the hand trick, all the fingers represent angles, and then you gave me ratios. Now I'm giving you a ratio, and you're giving me an angle. All right, here's the next one. This is just a different way to write the same thing. You may see arc sine, you may see sine -1. They still mean the same thing. They both mean inverse. So So here's what this says. What angle on the unit circle has a sine ratio of root 3 over 2? So take a minute, you show your hand, and you make it show root 3 over 2. For sine, what finger do you have to put down to make that happen? Your ring finger? All right, what angle is that? It's okay to think in degrees, so I'm thinking 60 degrees, but I have to put it within that range restriction. 60 degrees is pi over 3. Now I go back and I say it the other way. The sine of pi over 3 is root 3 over 2. All right, let me give you some other ones. Arc sine root 2 over 2. Arc sine root 2 over 2. Pi over 4. Good. Arc sine negative root 2 over 2. Negative pi over 4. Arc sine 1/2. Pi over 6. Arc sine negative 1/2. Negative pi over 6. Now you get the hang of it. I cannot take any answers for inverse out of the third quadrant. The third quadrant is what we call a dead zone. And in just a minute, when I draw the whole graph, I'll show you what I'm talking about with the third quadrant. But we don't take any angle values out of the third quadrant. Okay? All right, let's move on to cosine. Maybe this will click. The problem here is going to come if you do not understand the unit circle. If you can't do the hand trick, if you can't get the ratios, if you don't know the radian measure for degree measure, etc. This is really going to be tough. But for some people, this finally makes sense. It helps you understand what you're talking about when you're asking for ratios and angles. So now I'm looking at the cosine function. This is just the parent function for cosine. We graphed this. However, when we graphed it, we started at 0 pi and we ended at 2 pi. And we knew that the domain for cosine, for the cosine function, the parent function, it was all real numbers, remember? It goes on and on forever in a horizontal direction. And what did we say the range was? Highest number was 1, lowest number was -1. Okay, good. Well, I need a function that is 1-to-1 in order to have an inverse. So first I do the vertical line test. Passes that, no problem. Then I go to the horizontal line test, and again, at the peaks and the valleys, I have problems. So what area can I restrict my answers to such that I can find an inverse for cosine?
Between 0 pi and pi.
That's exactly correct, between 0 pi and pi. If I just look at the values between 0 pi and pi, I now pass vertical and horizontal, and I have a 1-to-1 function. What you're doing, this calculus idea, is that you are setting limits. You went from full playing field, right? All real numbers. Well, that won't work in this scenario, but instead of saying, oh, sorry, cosine doesn't have an inverse, you can say, wait a minute. Cosine does have an inverse if what? If we restrict the range to 0 pi pi. It's the difference between saying, oh, no, sine doesn't have an inverse because it fails the horizontal line test. Just saying, nope, sine does have an inverse if I restrict the range to negative pi over 2 to positive pi over 2. Okay, basically what I'm doing by doing it this way is I'm allowing a quadrant for all positive values. So notice that so far, both sine and cosine have gotten their positive values from quadrant 1. Right? For cosine, the negative values are going to come from 0 pi to pi. So where would the negative values come from? The second quadrant. And where did the negative values come from with sine? The fourth quadrant. So I'm allowing a location so that each trig function can get a positive ratio and a negative ratio. But I'm simply restricting the third quadrant completely. Okay. All right. Well, let's look at that. if the domain if the range on the cosine function was from -1 to +1, now that's the domain of the inverse function. And originally, the domain of the cosine function was all real numbers, but we've had to restrict it. We restricted it to 0 to pi, inclusive, which means that 0 is okay and pi is okay. Yes?
Can you go back on it?
So here?
Yeah.
Okay.
So what would happen if you instead like restricted it from pi to 2 pi?
That includes the third quadrant, which is not allowed. I see what you're saying visually. Visually, Cameron's saying, you know what, we could get the same inverse function, that 1 to 1-ness, if I go from pi to 2 pi, but if I do that, I've hit that dead zone, that third quadrant, and we stay out of the dead zone. Okay? All right, so let's take an example. This first one says, what angle on the unit circle, has a cosine ratio of 1/2? So you use your hand and you make your fingers work so that you see cosine of 1/2. So what finger goes down? Your ring finger goes down, and that is 60 degrees, but we're not working with degrees, so we turn that into radian, and that is pi over 3. Perfect. Then you think backwards. You think, okay, pi over 3 has a cosine value of 1/2. So you can easily check your work by working in the other direction. Let's try another one. This says, what angle on the unit circle has a cosine ratio of -√3/2? So again, you use your hand and you make it show cosine √3/2. Is that a 30-degree angle? Yes. But I need a -√3/2. -√3/2. So where on the unit circle can I get a negative cosine? I can get it in the second quadrant, because the third quadrant is the dead zone. We stay out of the third quadrant. So what angle has a 30-degree reference angle in the second quadrant? It's 150. And so 150 would be 5 pi over 6. And then you go backwards and you say, what is the cosine of 5 pi over 6? It is -√3/2. I suspect that if you're totally lost, brain exploded, you just don't yet know the unit circle well enough. You don't know the ratios, you don't know the angle to radian conversions, and you're still a bit lost with that. You got to get a handle on that first before this makes sense, because this requires for you to take that and work it backwards. Okay, so we've done sine, we've done cosine, now we have to do tangent. Yes, Adam.
Okay, so the second part of the picture that's in black, why is that there?
That's me basically trying to tell you how to turn it around to make sure it's correct. So it's undoing the inverse.
Oh, so basically you're turning it around to show how the thing is actually.
Correct. So I'm undoing the thought process. Originally what I was saying to you is, what is sine ratio for 45 degrees? And you were giving me a ratio. Now I'm giving you a ratio, and you're giving me the angle. So I'm taking you back. What's in black right here takes you back to what we started with. I'm giving you the angle, I'm telling you what I want, and you're giving me the ratio. What we're doing now is backwards. I'm giving you the ratio, and you give me the angle.
So is the answer up there?
So the answer is 5 pi over 6.
Okay.
That is the correct answer, because this says what angle on the unit circle has a cosine value of -√3/2. So your answer should be an angle in radian measure. Okay, in terms of pi. Okay, let's do tangent. Yes, ma'am.
So why is it that none of them are negative? Neither one.
It's not that none of them are negative. It's just that third quadrant is an area that we just don't delve into as far as limits are concerned. We stay out of there.
I mean, like, for, like, the arc cosine of, like, negative root 3 over 2, why is it that it's not negative 5?
Oh, well, where is the cosine negative root 3 over 2? I can go into the first quadrant or the second quadrant. Second quadrant is where cosine's negative, right? That value is 5 pi over 6. It doesn't need to be negative 5 pi over 6. Where does negative 5 pi over 6 put you? Mm-mm. Yeah, I can't be there. That's the dead zone. Now, I don't know if y'all heard her question. She said, why could that answer not be negative 5 pi over 6? For the previous problem that we did, negative 5 pi over 6 is really negative 150, correct? If I think about it in terms of degree and I go in a clockwise direction, where does negative 150 put me? In the third quadrant, which is the dead zone. I have to stay within the quadrants where I'm allowed. So, well, it is basically a matter of how we're setting our limits. And all of our limits involve the first quadrant, second quadrant, and the fourth quadrant. We just stay out of the third quadrant.
So Ms. Thompson, so arc sine is first and fourth quadrant.
Inclusive.
Inclusive. And then arc cosine is first and second.
Inclusive. Anybody want to take a guess at tangent?
Well, it already has to.
So everything is two quadrants, so it can't be second and fourth because that would go through. That would require that you go through the first, so that would be three quadrants. But you would fail the horizontal line test if you went three quadrants. It is first and fourth. Do you think there's anything different about it as compared to sine?
Oh, the arc is diagonal. Oh,
The line, the inverse tangent is going to be horizontal. That's true, but that didn't answer my question. What's different about the range for inverse tangent as it compares to the range of the inverse sine?
the range.
You're right that it's in the first and fourth quadrant. Well, let's look at the picture. This is the picture of the parent function. You're right. Cameron's right. So if I look at this picture, this is just a bunch of tangent graphs, so a bunch of periods graphed. And you can see that I have a problem again with the horizontal line test because I'm going to pass it in several different places. Unless I restrict it. And I'm restricting it right here from negative pi over 2 to positive pi over 2. But here's the difference. When I restrict this time, this has parentheses, so it is not inclusive. Is that what you said, Luke? Good. So here's the difference. This is interval notation, and when I use brackets, that means that I'm including those numbers in the brackets, and when I use parentheses, it means that I'm not including those numbers. So, since the domain of tangent has to be restricted, the domain of the tangent function was restricted. Remember, it was restricted. Negative pi over 2, positive pi over 2, we had asymptotes. That means now the range is restricted. Since the range of the tangent function was all real numbers, now the domain of the inverse is all real numbers. We actually don't have to graph that in here. That will come next year. That'll come in your calculus class. We're going to be graphing limits.
Wait, can you teach that?
I'm going to show you how to do it on your calculator, yes.
On our calculator.
Yeah, I am going to, honestly though, Kamala, it's not too hard to graph because here's what you do. So listen, you guys know what the restrictions are? Just graph that part.
Oh, so it's like you can look around and then just chop it off.
Yeah. And you can think all the cosine graph, and then you chop it off. You think all the sine graph, and then you chop it off. And then tangent, you have to actually rotate. Because it was going up and down, and now it's going this way. Okay, and I'm going to show you on your calculator. That's why I have to get calculators out. So let's practice some of these arctangents. First example says, I'm going to translate this for you again. What angle on the unit circle has a tangent ratio of √3/3? So then we go all the way back when I was first teaching you unit circle, and I said 30 degrees has all the threes, 60 degrees is just √3, which means that the answer to this question is a 30-degree angle. But I need to put it in radian measure, so that must be pi/6. And then, Tyler, if I think about it backwards, pi/6 is the angle whose tangent is √3/3. Yes.
Check yourself. Can you just like plug that in your calculator and then check to see if you have it right?
So tell me what you would plug into your calculator. Show me how you would do that in your calculator, and then I'll answer your question.
Tangent, and then do radical 3/3.
Okay, I like what you're saying so far, and then you hit enter.
And then it gives you decimal, and then it's like my answer was pi/6. I'll put pi divided by 6, which is going to be.
That is correct. As long as you understand what she just did. She understood that the answer that she got in the calculator had already been, the pi was already out of it. Like they did pi divided by 6 in the calculator. So as long as you take pi divided by 6 and get an equivalent decimal, then you're okay. But that's for checking your answer only, because all of these answers, with the exception of the times when they give you ratios that are not on the unit circle, they're on a circle, they need to be exact. So let's try another one. Where on the unit circle can I find a tangent ratio of √3? So 60 degrees, and 60 degrees is pi/3. Yeah. Okay. Now I want you to draw this on your paper, because I think this will help you. I think this will help you figure out where your answers are okay. So this is kind of your guideline for right now. This is like you're learning to play a new sport, and you have to know what's inbound and what's outbound, what's in play, what's out of play, what's going to get you into trouble, where you can play. What are your limits? It's basically what we're doing, Cameron.
So when I plug that into my calculator, just getting the degree.
Yeah, you just get 30, and then you know that tangent.
Okay, but your calculator must be set in degree mode.
Okay.
So if you set it in radian mode, like Caitlin had hers, you'll get a decimal value. Okay? You can switch back and forth. Listen, when you guys get in your car to come to work and come to school in the morning, you don't have to have somebody tell you whether to put it in drive or reverse. You shouldn't have to have somebody tell you whether to put your calculator in degree or radian. You should be able to figure that out. Okay, it's just really that simple. If you see a degree mark, put your calculator in degree. If you want an answer in degree, put your calculator in degree. If you put your calculator in radian, you must realize, though, that pi/6 has already been divided, and you'll get an equivalent decimal. Okay? All right, so what I want you to sketch here is just your x and the y axis. And let's just label some things. Okay, and I don't really like using red, but I'm kind of stuck with those colors since I'm not on the smartboard right now. Let's label this as 0 pi, and this is pi/2, and this is pi. But based on what we're doing, I don't want to label this bottom 3 pi/2. I want to label it as negative pi/2. Now, do you see why we did the coterminal angles first? Okay. Now, what I would have done if I'd been on the whiteboard is I would have labeled the third quadrant as the dead zone in red, but let's label it in black. It's the dead zone. That way everything else can be in another color. This is the dead zone. Nothing comes out of here. Okay, I'm just going to start with green, and I want to do sine first. And I want to show visually where I can get my answers, what range my answers would be for sine, for inverse sine. So what I'm going to do is close circle all the way up, close circle, and label it arc sine.
So it's not on the.
It is, that's why I've got the closed circle. So pi/2 is an okay answer. negative pi over 2 is an okay answer. I just didn't take it all the way up. All the way up. Pi over 2, negative pi over 2. All right, now let's do cosine. I'll do cosine in blue. Where should cosine go? 0 pi. I'm starting it here at 0 pi. 0 pi is an okay answer. And I'm going all the way over to pi. And that's arc cosine. Okay, now, last one we need to do is tangent. How is tangent going to look different?
It's not going to be a close.
It's not going to be a closed circle. I'm just going to do open circle. So I'm just going to start it here. Open circle, all the way here, open circle, and that's arc tangent. So it does not include pi over 2, and it does not include negative pi over 2. Open circle at those values. So this is kind of your rule book for right now. When you get your answer, which will be an angle, you need to check it against the rule book and make sure that it's a legal move. If somehow you find that you have an answer over here in the dead zone, you need to adjust. If somehow you find your answer is in the fourth quadrant, but it doesn't fall between 0 and negative pi over 2, you need to adjust it. Okay? Yes, ma'am.
So arctangent is basically the same as arcsine. Circles are.
That is correct. It is not inclusive. The circles are open. And if you think about it, when we're looking at the tangent function, what's the tangent function at pi over 2? What is tangent of pi over 2? It's undefined. What's tangent at negative pi over 2? It's undefined. It's the same line. It has to be undefined. So I can't include those values in the inverse if the initial function is undefined at those values. Okay? All right. So now we're going to do what Kamal was talking about. I just want to show you what they look like in your graphing calculator. So if you set your calculator to radian mode, and go to y equals and put in inverse sine. Now a little trick: if you'll hit zoom 7 before you graph, it'll automatically graph it and adjust the window for you. So put it in y equals and then go zoom 7. You have to be in radian mode. Zoom 7 resets your window. Because you would put the X. You have to put an X in. You can't just put. It opens up parentheses and you have to put the X in there. You get it? Everybody get it? Okay, good. Let's try cosine. So, Kamal, what you hopefully you're noticing is that from the original function, what was the x is now the y, and what was the y is now the x. All right, now tangent looks the most different. What was the x is now the y, what was the y is now the x. So if I started out with a table of values, like you guys did when you were graphing sine and cosine, you wanted to graph the inverse, you would just stick to the interval that you know is the range and graph those values. That's what you would get. Now, as far as what we have to do for this course, that's kind of it as far as graphing is concerned. We don't have to graph the inverses, but we do need to be aware of what they look like. We need to be aware of how to look at them if we need to look at them. So this is enough for what we're doing in here. I'm sure that when you get to Mulkey's class next year, Miss Lissam's class next year, they'll go way beyond this. But at least you know how to set your calculator to radian mode, how to do the zoom trig, and what the limits of the inverses are. Okay? Okay, so now what happens if I need to find an angle whose ratio is not something I know on the unit circle? Okay, I can find any angle on the unit circle as long as I'm aware of the ratio. Is it something that's from a 30, 60, 90 triangle, a special right triangle? So a ratio of 1/2, got it. Root 2 over 2, know what that is. Root 3 over 2, good. Root 3 over 3, all those I got because those are on the unit circle that I'm aware of. But what happens if I have to find the angle whose ratio is not something that I can make with my hand? What if they don't even give you a ratio? What if they just give you a decimal? You can plug that in too. You don't have to convert it, you can plug it in like it is. So here's our first example. First, set your calculator to radian mode. Okay, this is really going to take some kind of working through for some people to understand why this answer is what it is. So, the question says, what angle on the unit circle has a cosine ratio of 0.75? Okay, so let's back out of that and turn that into a fraction. What angle on the unit circle has a cosine ratio of 3 over 4? Can you make that with your hand? I can't make that with my hand. So I kind of have several options. One option, and we will do that in just a minute, is to build the triangle. And then do an inverse trig function to get the angle, which you guys already did in the last website on the tree problem. Remember? Okay, so let's just kind of do this for just a second. That says, what angle on the unit circle has a cosine ratio of 0.75? I can turn 0.75 into a fraction by making it what? 3/4, okay? Always drawing my angle from the origin. This is my angle in question. Cosine ratio is x over r, x over r. That question says, what is that angle that has that ratio?
What? How did you know that? Yeah, where's the 5?
Oh, this should be a 4. Sorry. Okay. What angle on the unit circle has a cosine ratio that is 3 over 4? How would you do that? If you had this problem, you did it 2 quizzes ago. What trig function do you see from that angle perspective? Adjacent over hypotenuse. What trig function is adjacent over hypotenuse? Cosine. What would you have done in the calculator to get that angle measure? You would have done inverse cosine 3 over 4. You did it 2 quizzes ago. Yeah. Inverse cosine 3 over 4. All right, do that in your calculator and put it in degree mode for right now, just so you kind of get an idea of what you're doing. Put it in degree mode so you can see the actual angle. What'd you get? 41.4. So then my angle in question is 41.4 degrees. So I could work this backwards and say, in my calculator, cosine of that answer. So do cosine second answer. Cosine second answer. Don't cut it off, just do cosine second answer. What'd you get? 0.75. Okay, now put your calculator in radian mode. It's like second and the little negative sign. Got it? Okay, so you're in radian mode. Now put in inverse cosine 0.75. Did you get this 0.7227? Okay, so let's do something. On the unit circle, if this is 0 pi, then that has a value of 0, right? If this is pi over 2, what is that numeric value? 3.14 divided by 2. Take your calculator and do that. 1.57. Good. This right here is 3.14. And what is this? Negative 1.57, based on the way that we've been doing the restrictions. This value is 0.7227. So where is it located?
First quadrant.
Somewhere in the first quadrant. So I know my angle is going to be between 0 and 90 degrees. How in the world can it be 7.7227? Okay, so here's what you do. You take 41.4 degrees. You turn it into a radian measure. What's your conversion? Pi over 180. Okay, so take 41.4, multiply it by pi, divide that by 180. What'd you get? The same number. When you are in radian measure in your calculator, the difference is the calculator has already multiplied whatever that is by pi. It's the same measurement. Are you lost? Okay, well, if you're going to put in 41.4, you need to be in degrees. 41.4 degrees, right? Well, what's your conversion to go from degree to radian? So multiply it by pi, or actually multiply that by 360, since you're in degree. Multiply it by 360, and then divide by 180.
So is that just a check? I gotta say.
I'll come help you in just a minute. Yeah. No, you're gonna, y'all listen to Tyler's question. She said, is there a way that you can do this so that you're not constantly switching? Not really. You have to be aware of when your answer needs to be in radian and when your answer needs to be in degree. I think, Tyler, though, that a lot of students understand the concept better if they'll work in degree. Just keep in mind that your answers need to be in radian. But I like a frame of reference being in degree. All right.
You could like work in like degree and then.
You can work in degree and then convert your answer to radian. Absolutely. All right, let's try another one.
That's the answer.
That's the answer. In radian measure. Do this one. Arc sine 0.19. Can you make a ratio out of 0.19? I hope you can. 0.19, make a ratio. 19 over 100. Right? Okay. So what it's saying is, what angle on the unit circle has a trig sine ratio of 19 over 100? So opposite over hypotenuse would be 19 over 100. I want to know what angle has that. Well, I can't make 19 over 100 on my hand. That means it's okay to use my calculator. So I go to my calculator, put it in radian mode. So I want my answer in radian, and do inverse sine 0.19, and you get this value. Now, that is the answer. Now, I want you to try it in degree mode so that you know what degree 0.19116 really is. It's about 10.9 degrees.
So you're gonna ask us for like the degree of.
You'll be working in radian measure. I want you to know how to convert so that you have an idea of where you are on the unit circle. Okay? I mean, otherwise you're looking at that going 0.19, what is that? Well, 0.19 is the radian measure, no longer in terms of pi, for about 10 degrees.
So if you multiply that by 9, technically it's getting close to 100%.
That is correct. Okay, one more. Arc sine 2.5. Why am I getting an error message? Yes, very good, because it's over 1. We cannot make a sine ratio such that the hypotenuse is less than the other sides, right? Think about it. This says sine is 2.5, so let's turn that into an improper fraction. What would that be? 5 over 2, correct? What is the sine ratio? It's opposite over hypotenuse. So that makes 5 the opposite and 2 the hypotenuse. That can't work. Why not? Hypotenuse is supposed to be the longest side. That's why you're getting an error message. So you just put no solution. Okay. We still have 2 more things to cover, so you guys are just gonna sit tight. All right, the next thing that we're talking about is composite functions. Composite functions. You probably did composite functions in algebra when you did f of g, or g of f, or f of f. And they were kind of a nightmare, really. Some students really struggled. These are very easy. These are much easier to do than polynomial composites. So the key to working with these composites is to remember that you need to work from the inside out. You always start with what's on the inside and you work your way out. So on this first example, I would do the inverse of the function first, and then I would do what was on the outside. Over here, I'm going to take the function, do this in the inside, and then find the inverse. And it makes much more sense when we put it in application. So, right, you don't have to write any of this because you already have it, but I wanted to show you, this is the notation that I suspect you've been using. For interval notation, what we were doing earlier, you probably have been using this, am I correct? This is function notation. Either way is fine. It's just much simpler to write it in interval notation. So this is just a review of what we talked about earlier, the domain and range of each of the inverses. This is for sine, this is for cosine, this is for tangent. So do you remember what they all were? You should have them on your paper somewhere already. We just wrote them in interval notation, and this is function notation. Yes, they do, with one exception. I've got some examples to show you. All right. So remember what I said, work from the inside out? Okay. So what this is saying is, what angle on the unit circle has a tangent ratio of 4/1? Well, can you make that with your hand? No. So that it's okay to put it in a calculator. Put it in radian mode. First do inverse tangent 4. And you get an answer. Okay? Now, find the tangent of that. It's 4. So Kamal made a comment earlier. He said, so basically, the inverse and the function just cancel each other out, which is true to a point. I'm going to give you a counterexample to that in just a second. All right, here's another example. First, I say, what angle, or what is the sine of negative pi over 2? So I go down to negative pi over 2. What is the sine? It's -1. Agreed? Then I say, where on the unit circle, what angle on the unit circle has a sine ratio that is -1? Negative pi over 2. So in that case, he's correct. They just cancel each other out. Okay, but here's my last example for this. And this is the counterexample to the general statement that he made. In this case, I cannot simply cancel out the sine and the inverse and make my answer 5 pi over 3. Why not? It's outside of the range restriction for sine. Sine can be from negative pi over 2 to positive pi over 2. Where is 5 pi over 3? What's 5 pi over 3? Give me the degree of 5 pi over 3. 5 pi over 3, isn't that? Anything over 3 is a 60-degree angle. 300? 300. Okay. 5 pi over 3 is 300. Why can I not simply cancel those out and leave my answer at 5 pi over 3? 300 is outside the range restriction. What's another way I can name that angle? Negative pi over 3. Within the restriction. So yes, in a way, come on, you can think about it that way. The inverses and the function cancel each other out, but only if,
So as long as it stays.
as long as that stays within the restricted area, you're fine. If it goes outside the restricted area, you have to adjust it and put it back in the restricted area.
What if it's in the depth?
It won't be infinite. No, but it does have a solution. Negative pi over 3 is the answer. Negative pi over 3 is the answer. All right, we got one more example. We got through all of this in 55 minutes in all the other class periods. We did the whole thing in all of the class periods, so we got to get finished with all of it. All right, last one. This says find the exact value. When you write this down, I want you to underline the fact that it says exact, because this is what's going to trip people up. Exact means I can't use my calculator to just do this as you see it. So it says the tangent of the arc cosine 2/3. So remember what I said, you work from the inside out. All right, so the inside part says what angle on the unit circle has a cosine ratio of 2/3. Can you make that with your hand? No, you can't. But it wants an exact value. So what should I do? You did this 2 quizzes ago. Build a triangle. Build a triangle. So that's what I'm going to do first. And I'm thinking, all right, I know that I've got to be in the first quadrant to make a positive cosine because that's where my restriction is. I know cosine is positive in the fourth quadrant, but I'm not going to build it there because that's not part of my range restriction. So I build it in the first quadrant. I know the cosine ratio is adjacent over hypotenuse, so I'll have a 2 on the x and 3 on the hypotenuse. And how do you find the y? So it'd be 2 squared plus something else squared equals 3 squared. I just worked it backwards. And so I get square root of 5. Now here's the thing. Honestly, I don't necessarily have to find that angle. If you're curious, you can. But the middle part says, find the angle whose cosine ratio is 2 pi over 3. You found it right here in this drawing. If you're just dying to know what the angle is, go ahead and put it in the calculator just to find out. But that answer comes from the outside part. Now, what is the tangent at that same angle? What's the here's the angle. The angle always comes from the origin. That is a Greek notation for mu. It's just kind of the bottom part is cut off a little bit, but that's mu. What's the tangent ratio? Opposite over adjacent. Root 5 over 2. That's your answer to this question. Now, had this not said exact value, what could you have done when you realized you couldn't make it on your hand? The calculator would be okay. Because it said what is the exact value. The only way to get those exact values is you gotta sketch the triangles out. Okay? Alright. The good news is this is it as far as what the inverses have involved. And we're gonna practice tomorrow. And we'll probably practice a little more on Friday. And the key to the worksheet